There we go. All right. Symmetry and transformation. So we're going to talk about, and we won't go through this all because it's 6 pages, but that's okay. We're going to talk about basic symmetries. First, we're going to talk about reflections. When we talk about reflections, that's flipped over the x-axis, meaning you go from, if I can hit the thing of it up, meaning you go from above it to exactly the same distance below it. So x comma y would be the same as x comma negative y when you reflect it. So if this was 3, you'd reflect it down to negative 3 while the x value is still shared as whatever number it is. Okay, another type of reflection is reflection across the x-axis. Excuse me. Same thing, except for in this case, the dot is reflected the same distance across the y. So this value here, which I didn't draw that line last time, so I won't this time. It can be whatever it is. This would be like 2. This would be like negative 2. Okay? That'd be like a point xy going to negative xy. That is a reflection across the x-axis. The common function is any function that is symmetrical to something is y equals x squared, because if you were to draw it, the basic graph, if I can draw a straight line, looks like this, right? Ooh, maybe if I can finish it off. If you were to reflect that, such that this side came over here and this side came over here, it would land on itself. That's how you know it's symmetric. So, it is considered symmetric when we can plug in a value and get the same thing out, whether that number be positive or negative. So like here, if I plug in 5 for y, or you can plug in a negative y like it says, I'm still going to get the same thing because negative y squared is equal to a positive y squared, so it's the same function. Right? Negative y times negative y equals just a y squared, so it would be the same function. Therefore, it's symmetric across the x because the x is the one you did not manipulate. Okay? So that would be one of these where this is the graph, most likely. Okay? Where's the button I'm looking for? There it is. So you can find how this function is symmetric. Plug in a negative x. Since negative times a negative once again equals a positive, that is the same function, right? If it is, it has to be symmetric to the opposite variable, the variable you didn't mess with, so it's symmetric to y. Then you can do the same thing. Plug a negative y in there. Once again, it will work out, because it's an even power, that this ends up being just y to the 4th. So it's the same thing. So this one is also symmetric to the x. So the shortcut would really be, if it's an even power, it's symmetric to the opposite one. So if it's y to an even power, it's symmetric to the x. If it's x to an even power, it's symmetric to the y. This one is, well, this one's actually something we're going to get to in a second. This one is symmetric, just not in the same way as the other ones. And I'm just going to tell you the cheat because, you know, why do I need to go through all the details when you can just do the cheat, right? It's all Danny wants to hear. If you plugged in a negative for all of these, I'm just going to run through it anyways because I can. Oh, the negative power, or the negative power, the odd power is going to make sure those negatives stay. So you're going to end up with something like this. Oh, no, sorry. where all the signs are now changed. But since we should know that we can take a function and multiply both sides by the same number, and they're still equal, these functions are still synonymous. It's a good word, right? In this case, when they're all like this, when they're all odd, it's actually symmetric to the origin. This is also what we'll call an odd function, but I'll talk about that more in a second. There's a real easy way to tell it's an odd function, but like I said, we'll get to that in a second. So this one, once again, the shortcut is to look at the powers. If there's an even power, it has to be symmetric to the opposite variable. Because when I plug a negative x in there, it's going to become just x squared. And so it's symmetric to the y. Okay, real easy way to tell if a function is symmetric to the origin. Look and see if, and that's not even the right explanation. This is the book definition. Here's the easy definition. All powers odd. And this is specifically on x, usually. Actually, only. And then even is the same thing. Powers are even on x. Okay? Real easy way. If they're even, we know they're symmetric across the y. And if they're odd, we know they're symmetric to the origin. So, and note right here somewhere that numbers are considered even powers because 0, which is how many variables you have there, is technically an even number, not an odd number. So that's necessary for both of these because if you have like x to the 7th minus x to the 5th minus x plus 4, that is now a neither situation because I have an even power with 3 odds. So that one was not is neither even nor odd because of that plus 4. Vertical and horizontal translations. We will do the vertical and we'll save horizontal for next time. You should already know these. But when a number is added to the outside like this or subtracted, all that does is move the graph up or down that many numbers. So you got to know your basic graphs. X squared, hopefully you know, is a parabola. So if this graph, I would do like this. I draw my little thingamabobs. I would go up 2. And then go over 1, up 1, because 1 squared is 1. And we can go through that more if you don't understand that. But I talked about that in Algebra 2 quite a bit, so hopefully we understand it. If we don't, once again, we can cover it again. Just ask me. But that is the graph. Here, on the next one, you need to know that x cubed looks like this. So a negative 1 takes the graph and moves it here. Then over 1 cubed is 1, negative 1 cubed is negative 1. So it should look something along these lines. Okay. Like I said, I'm going to stop there. I know I'm about 9 minutes or whatever, but we'll cover the horizontal translations next time. If you have any questions, once again, you can email me or ask me in class or before school, any of those times. Otherwise, have a good evening.